Good morning. Happy Thursday. We just have 2 days of school left, and so let's go ahead and press on through it. In this video, I want to summarize the material that we've talked about this week, the three gas laws that we've covered in honors chemistry. Those are Boyle's law, Charles' law, and Avogadro's law. Three really important gas laws that focus in on two particular variables that gases have, each one kind of different, and there's different things that remain constant, and they have these different equations. So I think it would be good to summarize everything so far. So in Boyle's law, Robert Boyle discovered that there is a relationship between pressure and volume, okay? And that relationship is actually an inversely proportional relationship. So as one goes up, the other goes down. But even more so, more than that, if you double one, the other one gets cut in half. If you triple one, the other one gets cut into 1/3, and vice versa. And so, a way that we could kind of represent that is this idea of, up and down by the same amount. I'm trying to draw those arrows the same size. That's important. Okay, an inverse relationship could be, one goes up a huge amount and the other one goes down a tiny bit. Okay, but if there is a corresponding proportional change in the opposite direction, that's an inversely proportional relationship. Okay, so what remains constant are the two other variables that gases can have. Robert Boyle was very much aware of the temperature aspect, okay? And he wouldn't have necessarily phrased it this way, but the number of particles or moles of particles of a gas get locked into place when you have a fixed sample of gas. And we represent that by the letter N. So N is the number of moles of gas, T is temperature, and of course P is pressure, V is volume. Now, to return originally to his discovery, he saw that at any moment for a fixed sample of gas at a fixed temperature, pressure times volume is a constant. And I'm going to represent that constant by the letter K. So that is a constant, and these are the variables that can kind of be changed as one goes up, the other one goes down. All right, and so again, you could kind of see that inversely proportional relationship. Let's say if you had, a pressure of 10 atmospheres or something, and the volume was, let's say, 5 liters, and well, that product is 50, right? 10 times 5 is 50. And it's kind of a weird unit, atmospheres, liters, but anyway, but that's the product. And, but what happens if you say, double or triple that pressure? Let's say if you double the pressure, right? So if we had 2 times 10 atmospheres and we double the pressure by pouring in some extra mercury into that device that Robert Boyle had designed, he would have seen that we get 1/2 the volume. It would have dropped down to 2.5 liters, and the product here is still actually 50 atmospheres liters. So again, don't worry about the units so much here, but the idea is we get a constant value, 20. This right here is 20, right? And this right here, oops, I should have put 1/2 times 5, my mistake, which is 2.5, right? We've got this factor of 2 here, and then a factor of 1/2 here. All right, we've doubled the pressure, we end up getting half the volume, and that's what was sort of at the heart of Robert Boyle's discovery. Okay, so 20 times 2.5. You still get that same constant, 50. That was his discovery. So pressure times volume is a constant. Now Charles' law. Charles' law investigated the relationship between temperature and volume. Okay, so as we heat up a gas, it expands, or as you cool a gas, it contracts. And if we use the Kelvin scale, we get a directly proportional relationship. That means as one goes up, the other one goes up, but not just any old way proportionally. So if you double the temperature, you double the volume. What remains constant here is pressure. You need a constant pressure for that to work out and a fixed sample of gas. Now, we didn't write it out this way in class, but you can also say that volume over temperature is a constant. And I'll use a different letter for this constant, just the letter B. Okay? So volume and temperature are the variables, and B is some constant. All right? Directly proportional relationship. Avogadro's law is another directly proportional relationship. And that's the whole idea, that if you change the number of gas particles, the volume's going to change proportionally, as long as you have a constant pressure and temperature. As you change the number of moles, the volume changes as well. And the equation for this law, V over N, is a constant. And I'll use the letter A here. Okay, so each time you have two variables, P and V, or V and T, or V and N, and combining them either by multiplying or dividing, these constants were discovered. Okay, now a law is something that is true. It's found to be true in nature. There's no real theory behind why necessarily. It's just observed to be true after a lot of experiments. Okay, so it turns out we can actually put all of these laws together in one single gas law. And that gas law is called the ideal gas law. And we'll talk about why it's called the ideal gas law tomorrow. But basically, it's a combination of Boyle's law, Charles' law, and Avogadro's law. The four variables are put together in one single equation. And so I'm going to go ahead and write out the ideal gas law, what it looks like, and then I'll describe for you why it's a combination of those three laws there. So the ideal gas law is written this way: PV equals NRT. And it's really easy to remember the formula for the ideal gas law. You just have to remember PIV-NERT, and you'll never forget it, PIV-NERT. So PV, that's like Boyle's law up here, P times V. Okay, so this part right here is like Boyle's law. N and T over here are the, of course, the other two variables. I need to talk about what R is, though. So this R value we have not seen before yet. So R is something called the universal gas constant. That letter represents something really important called the universal gas constant. Here we go, right there. And I suppose you could think of it as combining these gas constants all together. That's not rigorously true mathematically, but you can kind of think about it that way. It represents a constant value that shows up in any gas sample once you take into account all the other variables. So, another way to write the ideal gas law equation is to solve it for R, this universal gas constant, because it's actually a really important value. R here is equal to PV over N and T. Okay, and now hopefully you can kind of see how this is a combination of these three gas laws. P times V is up top, right? Right here you can see that's Boyle's law, right? And right here is Charles' law, V over T. And then right here is Avogadro's law, V over N. And so the three gas laws are kind of hiding together. And it turns out this ratio, PV over NT, no matter the gas sample, it could be a room filled with oxygen, it could be a helium balloon, it could be nitrogen under a lot of pressure. It turns out that that ratio is always a constant value. It's always a particular value, no matter your gas sample. Okay, so that's pretty striking, actually. There's this number, this gas constant value that's hiding in nature. And it has kind of a strange value. It equals, R equals a particular value, 0.0821, and it also has some particular units. You have to use some particular units when you're measuring these variables, but when you do measure them in atmospheres and liters and using the Kelvin temperature scale, we get atmospheres, liters over moles and Kelvin. So that right there is the value of a really important constant in nature, the universal gas constant, and it holds true for any gas sample. So no matter the gas sample, R shows up. Okay? And so we're going to have a little bit of practice to see how this ideal gas law works. But one particular application is to determine the molar volume of a gas. And often that's done at STP, standard temperature and pressure. So determine the molar volume of the gas. We can use the ideal gas law to figure out the volume of 1 mole of gas particles at standard temperature and pressure. So we take the ideal gas law, Pivnert, and we list out everything that we know. So we know that the pressure, standard pressure, is 1 atmosphere, exactly 1 atmosphere by definition. Volume we're about to figure out. The number of moles is exactly 1 mole because we're trying to find the molar volume, how much 1 mole occupies. So 1 mole exactly. Temperature, standard temperature is 0 degrees Celsius for gases by definition, which is 273 Kelvin. So with that, we can actually solve for the volume. There is one more letter, that's R, but we just talked about that. That's the universal gas constant, and it always equals 0.0821 atmospheres, liters, moles, Kelvin in the bottom. There we go. Okay, so let's plug in what we have here and solve for the molar volume of a gas. A really important result. We'll rearrange this equation for volume. Volume equals nRT over P. And so 1 mole of any type of gas times the universal gas constant with its units, kind of some funny units, atmospheres, liters over moles and Kelvin. Temperature in Kelvin is 273, standard temperature, divided by 1 atmosphere. Okay, so watch what happens with the units, by the way. Atmospheres divide out. Kelvin divides out. Moles divides out. And we're left with liters right there. And so, grab the calculator. Might take a moment for mine to load here. But not much to type in, because we have some ones in that fraction right there. Okay. Oh goodness, here we go. All right, so 1, come on. 1 times 0.0821 atmospheres, liters divided by moles, Kelvin, times 273 And then, of course, divided by 1 doesn't really change the value. Typed it in twice. There we go. And we get the really important result of 22.4 liters. 22.4 liters. The significance of this is that if you have 1 mole of gas particles, your gas sample will be 22.4 liters at STP. Okay, if you change the temperature and the pressure and you use different temperatures and pressures, you'll have a different volume. Okay, that's like Boyle's law and Charles' law, the effects of those. You know, you could compress that 1 mole into a smaller volume, or you could cool it so it occupies a smaller volume. But when you're at 273 Kelvin, 0 Celsius, and 1 atmosphere of pressure, that's the volume that your gas sample occupies. Okay, and so it actually leads to an important equivalence. 22.4 liters equals 1 mole of gas at STP. So important thing to remember. All right, let's look at some other examples of how to use the ideal gas law. What pressure is exerted by 0.7 moles of a gas at 25 degrees Celsius in a container with a volume of 1.5 liters? Let's list out everything that we know about this gas sample. The pressure is what we're going to try to find. The volume is 1.5 liters. N is the number of moles, it's 0.75 moles, and it's at 25 degrees Celsius, which is 298 Kelvin. Again, R is the value of the universal gas constant, 0.0821 atmospheres, liters over moles, Kelvin. And we can solve for pressure now. Pressure equals nRT over V. The number of moles here is 0.75. The universal gas constant is 0.0821. Atmospheres, liters over moles, Kelvin. And the temperature is 298 Kelvin. And the volume, 1.5 liters. So what is the pressure that this particular gas sample is exerting? So we got 0.75 times 0.0821 times 298 divided by 1.5. And it must be exerting right around 12 atmospheres, with 2 significant figures. Okay, the volume and the number of moles both have 2 significant figures. These values have 3 significant figures. We go with the smaller number of significant figures. Right. Okay, let's do one more, and then I'll let you do the third one on your own to finish up today's lesson. Find the volume of 0.85 moles of gas at a pressure of 520 torr and a temperature of 15 degrees Celsius. Again, let's list out everything that we know about this particular gas sample. We know the pressure. The pressure is 520 torr. Come on. We don't know the volume. We're going to find the volume. The number of moles is 0.85. And the universal gas constant is what it always is. It's a constant in nature. And temperature, 15 degrees Celsius. All right, so do you remember back in Charles' law, I tried to that we need to use the Kelvin temperature scale. And that's also true for the ideal gas law. And that makes sense, right? If we're going to combine these gas laws together, we need to make sure we're doing the same type of thing in the ideal gas law as we did up here. So it makes sense. If we need to use Kelvin, right? If Kelvin temp scale is used, we get this directly proportional relationship. We need to use Kelvin in the ideal gas law as well. Okay, and so again, we've got to add 273. So 283 plus 5 is 288. 288 Kelvin. Now, we also need to adjust the pressure into a new unit. And that's not because Boyle's law requires us to. Boyle's law and Avogadro's law, it turns out you can use any units of P and V and any units of V here. We need to use moles for N, but why would we need to change this unit for the ideal gas law? That's because of the unit in the universal gas constant. We only get this constant value when we measure these variables of our gas with these particular units. So we have to use the units that are in the unit of the universal gas constant. Okay, so if you don't have liters, you need to change it to liters. If you don't have atmospheres, we need to change it to atmospheres. So let's go ahead and do that. 1 atmosphere is 760 torr. That's good to 4 significant figures. So we'll divide 520 by 760 to have our pressure in atmospheres. Okay, and we get 0.68 atmospheres. 0.68. And I actually like to carry through 1 extra digit if it's not my final answer yet. So 0.684, I'm going to write that, but recognizing there's my uncertain digit. So now let's plug all of this in and solve for the volume of this particular gas sample. We're going to solve for, oh goodness, my pressure. Put that there and move that there. So let's rearrange the ideal gas law for volume. PV equals nRT, and we can rearrange it for volume. Volume equals nRT over P. The number of moles is 0.85. The universal gas constant is 0.0821. Atmospheres, liters over moles Kelvin. The temperature in Kelvin is 288. And the pressure in atmospheres we just found is 0.684 with an extra figure there. Let's type all that in. Our final answer will only have 2 significant figures though. Technically this is just 2 down here. All right, type it in. 0.85 times 0.0821 times 288 divided by 0.684. And we have 29. What is the unit? What did we just determine? 29 what? We just solved for volume. So should we just guess? Is this milliliters or gallons? What is it? It is the unit that's left over after all these other units cancel out. Liters. So 29 liters is the volume of our particular gas sample here. So to finish up for today, I'd like for you to try this last problem. I don't have a worksheet with this problem written out, so you'll have to write it out on your own. And there are some changes you'll need to make. Notice the units they've given you. They've given you torr, degrees Celsius, and milliliters. And we can't really use any of those units in the ideal gas law. We need to make sure we use atmospheres for pressure, Kelvin for temperature, and liters for volume, because those are the units in the universal gas constant unit. Okay, so give this one a try, and just for the sake of this problem, I'm going to put a decimal point right here so we can have 3 significant figures on everything that we're plugging in, and the answer can have 3 significant figures. All right, so try that problem, and then you'll be done for today. Bye.